So today we start with the connection between derivative and total derivative. So we know the definition of derivative. So let me recall it again. So f is a function from R2 to R. We are talking about derivative at a point x naught. So x naught looks like x naught y naught. So we say f is differentiable at x naught if this limit h going to 0, f of x naught plus h minus f of x naught minus f prime at x naught dot h divided by, that means multiplied by 1 by norm h, if this is equal to 0. Here f prime at x naught is a vector alpha beta, and we have seen in our previous lecture that what these alpha betas are. They are nothing but the partial derivatives at the point x naught y naught. Okay. Now what I want to prove is the following theorem, that if f is differentiable at x naught, then the directional derivatives at x naught exist in every direction. Okay, so let me again recall what is the definition of the directional derivative. So I take a vector u which looks like u1, u2, such that norm of u is equal to 1. Then the directional derivative of f at x naught in the direction of the vector u is called du f at x naught, and is given by the following limit t going to 0. Here t is a number, f of x naught plus tu minus f of x naught divided by t. This is the definition of the directional derivative. So all I have to show is, assuming that f is differentiable at the point x naught, I am going to show that the directional derivative exists in all possible directions. Okay. So derivative at x naught exists at x naught exists implies and implied by that limit capital H going to 0 modulus f of x naught plus h minus f x naught minus f prime at x naught, which remember is a vector, so it makes sense to take a dot product with h, where h looks like, I will write in the bracket here, h equal to h1 h2 divided by norm h. This is equal to 0. Derivative exists means this. So in particular, choose h to be t, where u is a vector, t is a number. The norm of h is nothing but mod t. because u is an unit vector. So while taking norm h going to 0, we can as well take t going to 0. So if instead of h I put tu in the above limit, what I get is that limit t going to 0 modulus f of x naught plus tu minus f of x naught minus f prime x naught dot the vector tu divided by mod t, this is equal to 0. Just in the previous limit I have put h equal to tu, but this then implies that limit t going to 0, since I have the modulus, it is f of x naught plus tu minus f of x naught minus t times f prime x naught dot u, because t is a number, divided by t, this is equal to 0. This implies limit t going to 0 modulus f of x naught plus tu minus f of x naught divided by t minus f prime x naught dot u is equal to 0. This then implies that limit t going to 0 f of x naught plus tu minus f of x naught, this whole thing divided by t is equal to f prime at x naught dot u. So the limit exists and the limit is equal to f prime x naught dot u. So it implies that if the function is differentiable at x naught, then partial derivatives exist in all, the directional derivatives exist in all possible directions. Not only that, it also tells me how to compute the directional derivatives. So for that, I will just put it as a remark, and I will start with a notation. Let us say f is from R2 to R. Then I define this. Its notation, it's called gradient of f at the point xy. It is just fx at the point xy comma fy. So it's a vector. And we know this gradient, if f is differentiable, this gradient actually gives me the derivative. So grad f at x naught y naught is nothing but f prime at the point x naught y naught, which is given by the definition of grad as fx at x naught y naught comma fy at x naught y naught. Now in this light, what I have proved is that if f is differentiable at x naught, which is little x naught little y naught, then for a unit vector u, I have du f at x naught, which is nothing but grad f at x naught y naught dot product with the vector u, which is given by u1 u2, where u equals to u1 u2. So that means to calculate the directional derivatives of a function, all we have to do is we have to calculate the partial derivatives first. Evaluate the partial derivatives at the point where we are going to talk about directional derivatives. Let us say that point is x naught y naught. So what I do is I calculate the partial derivatives at x naught y naught. Then I get a vector. If I look at fx at x naught y naught, comma fy at x naught y naught, then I just take the dot product of this vector with the vector u1 u2 in whose direction I am calculating the directional derivative. This quantity gives me the directional derivative of the function at the point x naught y naught. Okay. So this comes very simply, but some care has to be taken here that just the mere existence of the gradient vector, that is grad f, does not give me the existence of the total derivatives, the existence of the directional derivatives. For that, let me just look at this simple example. See, you might think it this way, that suppose I know that I can calculate the gradient of a function. That means f has partial derivatives. Once I have this, then if I believe the previous theorem, then the directional derivative of the function in any direction should exist as grad f dot u. But then we are forgetting the first line of the theorem, that if f is differentiable at x naught, then it is true. If f is not differentiable at x naught, grad f may exist, but the directional derivatives in many other directions may not exist. So that is what we are going to see in this example. So let us look at this function f of xy to be equal to x by y if y is not equal to 0. It is 0 if y is equal to 0. Let us look at this function. And now I want to talk about its partial derivatives, directional derivatives and all such things. So I take a vector u, which I call u1, u2. Then I want to calculate limit t going to 0 f of, I am going to calculate the directional derivatives at, let us say, 0 0. So it is 0 0 plus t u1 t u2 minus f of 0 0 divided by t. What I get is limit t going to 0 f of t u1 t u2 divided by t. Okay. Now I say this is 0 if u1 equal to 0, but u2 not equal to 0, and this is also 0 by definition if u2 equal to 0, and this is equal to u1 by t u2 if u1 u2 both non-zero. That means if I look at the third case, it is very clear that as t goes to 0, this limit does not exist. But in the other cases, the limit do exist. Now what are the other cases? I take u1 to be equal to 0. That means what I am getting is a vector in the direction of the y-axis. If I take u2 to be equal to 0, I get a vector in the direction of the x-axis. Those two directional derivatives exist. But if u1 and u2 both are non-zero, then I get vectors in different directions. In those directions, the limit doesn't exist. So the conclusion is that directional derivatives in all directions does not exist, but grad f at 0 0, which is given by fx at 0 0, fy at 0 0 exist. So why it doesn't contradict the previous theorem? Simply because the function is not differentiable. So this is something to remember, that if the function is differentiable at x naught, then to calculate the directional derivatives, which now I know exist if f is differentiable, to calculate the directional derivatives in any direction, all you calculate is the gradient, that is grad f at the point, and take the dot product with the vector u1, u2. That will give me the directional derivative of the function in any direction. Now so far whatever we have developed goes through for arbitrary Rn. So in particular we will concentrate on functions from R3 to R. So definition of derivative. This is similar as in R2. So is directional derivative. This is also similar as R2. Even gradient as in R2. So formally, what do I mean by f prime x naught here? So this should be f prime at x0, y0, z0, because I am on R3. So how is that defined? This is limit h1, h2, h3 going to 0, 0, 0. This is limit h going to 0 of the quantities f of x naught plus h minus f of x naught, exactly as in the case of R2, minus f prime x naught dot h times 1 by norm h, if this is equal to, if this is equal to 0. Here h is h1, h2, h3. Okay. And directional derivative is exactly as in the previous case. I can define d u f at x naught, y naught, z naught. This is limit t going to 0 f of x naught plus t u1, y naught plus t u2, z naught plus t u3 minus f of x naught, y naught, z naught whole divided by t, where u is the vector u1, u2, u3 with norm 1. Okay. So everything is analogous here. Whatever we have proved, all the results work, including the chain rule, okay, which I am going to use now. Now in all this, I could suddenly see that gradient of f is playing some role. So we want to understand the geometric interpretation of gradients. So that is what I am going to start with now. Okay. So we start with definition of curves. So what is a curve? In R3, it works similarly in R2 also. It is just a differentiable function c from an interval ab to R3. Then if I look at Ct, t belongs to ab, this is a curve. So it is just image of differentiable functions. So c is differentiable. Okay. Now I want to talk about the tangents to curves. How does one define tangent to a curve? Okay. So let us say I have a point. So C, let us say, is a curve AB to R3. Let us say T naught belongs to AB, and I look at the point C T naught. Okay, so the image of the curve, let us say, looks like this, and this is C of T naught. Okay, I want to talk about the tangent line at the point C T naught. So analogous to the one-dimensional case, I can tell you the parametric equation of the line in the space. It is given by, if I call it LT, this is the line which passes through CT naught, that is the point on the curve, with the direction of the vector C prime T naught. So it is T minus T naught times C prime T naught. So what I get is a line which passes through the point C T naught, because if I put T equal to T naught, then LT is equals to CT naught, and the direction of the line is in the direction of the vector C prime T naught. That's why C prime T naught is called the tangent vector. Sorry, this is at, so C prime T is called the tangent vector. So this would give you the direction of C prime T naught. With T, of course, the tangent changes. So the tangent vector is also a function of T, which I have written as C prime of T. Okay, now I need some more notations about planes. So how do we view planes? So what is a plane? We know the usual equation of planes. It is of the form AX plus BY plus CZ equal to D. Let us say X naught, Y naught, Z naught is a point on the plane. Then AX naught plus BY naught plus CZ naught, that is also equal to D. That implies A of A times X minus X naught plus B times Y minus Y naught plus C times Z minus Z naught is equal to 0. So then I can write this as the collection of all points X, Y, Z, such that the dot product of the vectors A, B, C dot X minus X naught, Y minus Y naught, Z minus Z naught is equal to 0. So any plane actually looks like this kind of a set X, Y, Z, such that ABC dot X minus X naught, Y minus Y naught, Z minus Z naught is 0, where X naught, Y naught, Z naught is a point on the plane and ABC are some given numbers. So any expression of this form always gives me a plane. Now this formulation of plane I am going to use. Now let us come back to tangent line again. Let us see an example. So let us look at the curve CT equal to TT square. Okay, where let us say T belongs to minus 1, 1. Okay, then what does the curve look like? This is clearly a parabola, y equal to x square form, so it looks like this. And I want to calculate the tangent line. Let us set the origin. Let us say 0, 0. So what would be the equation? Equation of the line should be LT equal to C of 0, because I see that C of 0 is 0, 0, plus t minus t naught into C prime t naught, that means C prime at 0. So I calculate what is C prime at t. It turns out to be 1, 2t. So C prime at 0 is 1, 0. So what I get is 0, 0 plus, here t naught also is 0, so it is t times 1, 0. So it is just t 0, where t varies over the set of real numbers. So all I get is the x-axis, which is very obvious from the picture, that this line at 0, 0 is the tangent to the curve. Okay, fine. Now I define something called surface. So what is a surface? So I would say surface in space. Let us say f is a function from R3 to R. F is differentiable. Okay. I look at the set S, fix a constant C, fix some, let us say, D in R. I look at all x, y, z which are mapped by F to D. Okay. I call S is a surface if grad f at x, y, z is not equal to 0 for all x, y, z in S. Okay. So what is a surface then? I have a differentiable function f. I fix a constant d. I look at all x, y, z such that f of x, y, z equals to d, assuming the set is non-empty, of course. Then if the gradient of the function at all those points x, y, z is non-zero, then I call S a surface. So some obvious examples of surface I can try to see. Let us look at the plane. Ax plus by plus cz equal to d. Is this a surface? So what I do is I concentrate on the function f of x, y, z equal to ax plus by plus cz, and then I look at all x, y, z such that f of x, y, z equal to d. Now we can see from the definition of f that this is the same plane given by ax plus by plus cz equal to d. Question is, when is this a surface? So for that I need to look at gradient of f at any x, y, z. Well, gradient of f at x, y, z turns out to be a, b, c. So my definition demands that this gradient should be non-zero. That means I want a, b, c to be not equal to 0, 0, 0. This would imply that one of the three quantities a, b, c should be non-zero. Okay. If all of them are 0, then I don't have the plane, you see. That means any plane is a surface. So let us look at another example. Let us look at sphere of radius, let us say some a, where a bigger than 0. Okay. For this, I look at the function f of x, y, z to be equal to x square plus y square plus z square. Then my sphere is just the collection of x, y, z such that f of x, y, z is equal to a. F is certainly differentiable function. All I need to check is that the gradient of f at every point on the surface is non-zero. So what is gradient of f at the point x, y, z? What I get is twice x, twice y, twice z. Okay. Now this should be not equal to 0, 0, 0. That means one of those x, y, z should be not equal to 0, 0, 0. Okay. Now what happens if all these quantities are 0? X, y and z both are 0. Then I am getting the point 0, 0, 0, which fortunately does not belong to the sphere, as a is strictly bigger than 0. Okay. So at every point on the sphere x square plus y square plus z square equal to a is strictly bigger than 0, the gradient is non-zero, because all these quantities cannot be 0 then. So any sphere of any positive radius is always a surface for us according to our definition. Okay. Now the next, let S be a surface and x naught, y naught, z naught. So it's a surface in space. Let us say this is a point on S. I want to talk about something called tangent plane to S at the point x naught, y naught, z naught. So first of all, it should be a plane. I will first tell you what is the definition of the tangent plane. Since S is a surface, S must be given by a function. So it must be collection of all points x, y, z such that f at x, y, z is some constant d. S must be of this form. I then look at grad f at x naught, y naught, z naught. So I know its expression, what it is. It is fx at the point, let us say capital X naught is equal to x naught, y naught, z naught. Then grad f at x naught, y naught, z naught is fx at x naught, comma fy at x naught, fz at x naught. Then the equation of the tangent plane is nothing but this, that fx at x naught, comma fy at x naught, comma fz at x naught, this vector dot x minus x naught, y minus y naught, z minus z naught equal to 0. So if I write it down, the equation of the plane turns out to be fx at x naught times x plus fy at x naught times y plus fz at x naught times z minus fx x naught times x naught plus fy x naught at y naught plus fz x naught times z naught equal to 0. Notice here that capital X naught, that is the points x naught, y naught, z naught is given to me. So fx at x naught, that is a number, fy at x naught is a number, fz at x naught is a number. So it is of the form ax plus by plus cz minus ax naught plus by naught plus cz naught equal to 0, which is certainly equation of a plane, because x naught, y naught, z naught is constant given coordinates of a point. So the portion in the bracket is actually a number, so it certainly represents a plane. And given a surface and given the points, I can certainly find out this plane. That we will do in the sequel. But the question remains is, why exactly this plane is called the tangent plane to the surface? Is the plane in some sense tangential to the surface? We will like to know this. So let us intuitively try to fix it out. So suppose this top portion is a surface, and at this point I want to write the equation of the tangent plane. Now I know the equation. I want to verify whether the plane is tangential to this surface. So what I do is I choose a curve, this is a curve, so this dotted portion is on the other side of the surface, and I will look at then the tangent lines. So if I take a different curve, I will get a different tangent. I will just like to check whether these tangents lie on the plane which I call tangent plane. So let us say S is the surface. Then I know that S is given by all x, y, z such that f of x, y, z is equal to d. Let us fix a point x naught, y naught, z naught belonging to S. I take a curve C. So C is a curve on S passing through the point x naught, y naught, z naught. It means then there exists T naught such that C of T naught is equal to x naught, y naught, z naught. Then I can try to write down the tangent line at the point CT naught. So whatever we have discussed so far, the tangent line contains the points x, y, z, which satisfies the following, that the vector x minus x naught, y minus y naught, z minus z naught, this is parallel to the vector c prime t naught. This is what is the equation of the tangent line, means x minus x naught, y minus y naught, z minus z naught is a scalar multiple of c prime t naught. So it is lambda times c prime t naught. On the other hand, since the curve C lies on the surface, I also have that f of Ct equal to d for all t in that interval. Let us say t belongs to AB. This one variable function I call ht. Since the function is constant for all t in AB, I know that h prime at t naught certainly is equal to 0. Here h prime t naught stands for the usual one variable derivative of h at t naught. Now I want to write down what is h prime at t naught. For that I need to apply chain rule. So what does this say? By chain rule then what I get is that I get del f del x at ct naught times c1 prime t naught plus del f del y at ct naught times c2 prime at t naught plus del f del z at ct naught times c3 prime t naught equal to 0, where what are these c1, c2, c3? Well, ct is given by c1t, c2t, because it's a curve in R3, c3t. But then this precisely implies that grad f at ct naught dot product with the vector c prime at t naught is equal to 0. Okay? But then this implies, since the vector x minus x naught, y minus y naught, z minus z naught is parallel to c prime t naught, I get that grad f at ct naught dot x minus x naught, y minus y naught, z minus z naught is equal to 0. Now if I expand this, what I get is exactly the equation which I had written here. Okay, where grad f at C2 is given by the first quantity in the parenthesis, that is, I just have called x naught is Ct naught. If I just use this, then what I get is the equation of the tangent plane. That means the tangents to the vectors Ct actually lie on the plane. That is why this plane is called the tangent plane. It consists the tangents to the curves passing through the points t naught. So let us see some examples now, whether it matches with our intuition. So first example, the obvious one, I take the sphere, that is, my surface S is all x, y, z, such that x square plus y square plus z square equal to 1. Question is, what is the tangent plane at the points, let us say 0, 0, 1. So let us look at the picture. So my sphere is this. Let us say this is the point, the intersection with the z-axis is the point 0, 0, 1, and I want to know what is the tangent plane. My intuition suggests that the plane should be looking something like it should be parallel to the xy plane just at the height z equal to 1. So the tangent plane should be the plane z equal to 1. Just think of a ball, and on the top of the ball you want to have a plane which is tangential to the ball. Just think like putting a postcard on the ball. Okay? So from the definition of the tangent plane, I am planning to get back that postcard, that is z equal to 1. So let us go by the formulas. So what is my f here? F of x, y, z is x square plus y square plus z square. then what is grad f at xyz? This is 2x, 2y, 2z. So what is grad f at 0, 0, 1? This is 0, 0, 2. Then what is the equation of the tangent plane? That is 0 times, that is fx at the point, times x minus x1, that means x minus 0, plus 0 times y minus 0, plus 2 times z minus 1 equal to 0. That means z equal to 1. This is the tangent plane. So it matches with our intuition. Okay. Now let us look at another example. Let us look at this surface. So S equal to all x, y, z such that x square plus y square minus z square equal to minus 1. Okay. So what is the surface then? I can try to draw this. This is actually two-sheeted hyperboloid. So look at the height 1 and minus 1, and there so this is my surface. Let me see whether I can find the tangent plane at the point again. I want to find tangent plane at, let us say 0, 0, 1. That means at this point. Again you feel like the tangent plane should be z equals to 1. So let us see what is my f x, y, z now. This is x square plus y square minus z square. So grad f at x, y, z then is 2x, 2y minus 2z. So grad f at 0, 0, 1, that is 0, 0, minus 2. And then the equation of the tangent plane at 0, 0, 1 is 0 into x minus 0 plus 0 into y minus 0 minus 2 into z minus 1 equal to 0. This implies again the plane is z equal to 1. What happens to the tangent plane at 0, 0, minus 1? So I have to calculate then grad f at 0, 0, minus 1. That means I get 0, 0, 2. Okay. Then the equation of the tangent plane is 0 x minus 0 plus 0 y minus 0 plus 2. Now it is z plus 1 because my point is 0, 0, minus 1 equal to 0. This implies the tangent plane is z equal to minus 1. Look back at the picture. The tangent plane at this point is certainly, it looks like the tangent plane should be parallel to the xy plane at the height z equal to minus 1. This is precisely what is coming through the calculation also. Let us look at one last example. I look at this surface 3xy plus z square equal to 4. I want to calculate the tangent plane at the point 1, 1, 1. What is the idea? I look at the function first. What is fxyz? This is 3xy plus z square. So my surface is actually all xyz such that 3xy plus z square equal to 4. So if I calculate it, grad f at x, y, z, that is 3y, 3x, 2z. So at the point 1, 1, 1, what I get is 3, 3, 2. So the equation of the tangent plane is then 3 into x minus 1 plus 3 into y minus 1 plus 2 into z minus 1 equal to 0. That is 3x plus 3y plus twice z, that is equals to 8. Okay, so far so good for tangent planes, but what is the geometric interpretation of grad f then? Well, I again look back at the equation of the tangent plane. So it is grad f at x naught times x minus x naught, y minus y naught, z minus z naught. This is equal to 0. Okay. Now x naught, y naught, z naught is a point on the tangent plane, and so is x, y, z. But grad of f is equal to 0. That means grad f at x naught is a vector which is orthogonal to the tangent plane. This implies grad f at x naught, I would say, is perpendicular to the tangent plane. Because if we know that if dot product of two vectors is 0, then the vectors are perpendicular to each other. I am using the same technique here, that if I take any vector in the tangent plane, then the vector grad f is perpendicular to that. That means the vector grad f x naught is actually perpendicular to the tangent plane. Let us look back at the previous example again, which I have computed here. What was the tangent plane in the first case? I got z equal to 1. Okay. Then what was grad f at 0, 0, 1? That was 0, 0, minus 2. So the direction was this. It was going in this direction, and the tangent plane was this. See? So grad f is actually perpendicular to the tangent plane, which is apparent from this equation also, that the dot product of the vector grad f with the vector x minus x naught, y minus y naught, z minus z naught is 0. So it is perpendicular to the tangent plane. That's why grad f x naught at the point x naught is called the normal to the tangent plane at x naught. So what we got, the geometric interpretation of grad f at x naught is a vector which is normal to the tangent plane of the surface S. Surface is all x, y, z, such that f of x, y, z equal to d at the point x naught given by x naught, y naught, z naught. So this is the geometric interpretation of the gradient, that it just produces the normal to the tangent plane of the surface at the point x naught, y naught, z naught. In the next lecture, we will move towards the mean value theorem for functions of several variables and look at the consequences of mean value theorem in these cases.